All right. Hey, everyone. Welcome back to another lecture. So this week's topic is going to be on number theory. We're going to go based off of what we did last week with divisibility and other properties like bases. We're going to go into a bit in modular arithmetic or the study of remainders. So as usual, our handout is posted on our website. You can go there to check it out. There will be some overlap between example problems and like some homework questions from last week, since some of the methods we will be learning this week will be much like more efficient at solving problems than what we learned last week. So we'll be going over what mods are, various operation in mods, the binomial expansion, modular inverses, as well as the Chinese Remainder Theorem. So our first topic will be what is a mod?
Okay, so a mod basically in simpler terms is a remainder. And there are a lot of formal ways to define mod. The easiest way to define a mod, so we have something, let's say A mod B. That simply means the remainder when you divide A by B. For example, if we wanted 25 mod 3, if we divided 25 by 3, we get a remainder of 1. So this is equal to congruent to 1 mod 3. And basically all the numbers which have the same remainder when divided by whatever the base is are called congruent together in mod B. And we express congruence with this triple equal sign. For example, we can say 1, 2, 3, 0, 2 is congruent to 2, 3, 2, 2. It's congruent to 17. It's congruent to 2 in mod 5. Because all of these numbers share the same common remainder of 2 when divided by 5. Let's go into a sample question. So given that today is Saturday, what day of the week will it be in 1,000 days? The key part to solve this problem is to note that the days of the week cycle in week 7, and we don't exactly care how many weeks have passed, just how many excess days. In other words, we want the remainder. So we want to find 1,000 mod 7, which with some division would get us that 6 as 1,000 is congruent to 6 mod 7. This means that moving forward 1,000 days is basically the exact same thing as moving forward 6 days, mod 7. And 6 days from Saturday, we can manually count out, is Friday. Additionally, we could have thought of this as moving back 1 day, as -1 is also congruent to 6 mod 7. So instead of going 6 days forward, we could have gone Saturday and 1 day back to get Friday. So an important thing to note from this problem is that negative numbers are just as valid for mods as positive numbers. So negative numbers work in basically the same way. For example, if we took -12 mod 5, that would be congruent to 3 mod 5, as it's 5 times -3 equals -15, and then plus 3 will give you -12. So the remainder is 3. This comes in handy later in later problems where canceling out is important. Next, we'll start looking at operations using modular arithmetic. So most of the operations that work in normal algebra work the same in modular arithmetic, namely addition and subtraction, multiplication, and exponentiation. So more specifically, if we have two numbers, a and b, that are congruent in some mod n, then a plus c is congruent to b plus c, and same with a minus c. Similarly, a times c is also congruent to b times c. And finally, if we raise it to some common term, a to the k is congruent to b to the k. And all this is mod n. So now we'll go through some quick examples to show how these work. For example, if we want to find what 3029 plus 1203 is mod 10, these numbers are small enough that we could just add them, but instead we could just look at the last digits. So in mod 10, 3029 is congruent to 9 mod 10, and 1203 is congruent to 3 mod 10. So instead, we can just take this entire expression mod 10 and get 9 plus 3 equals 12, which is congruent to 2 mod 10. Similarly, for subtraction, we'd take instead 9 minus 3, which equals 6, which is congruent to 6 mod 10. And then finally for the power, for the product, instead of, it works in basically the same way. We do 9 times 3, which is congruent to 7 mod 10. And if you plug this in a calculator, you'd see that this multiplies with the last digit of 7, which means that its value is 7 mod 10. And then finally for exponents work in a slightly different way. So one might think that you could simply replace the 1, 2, or 3 with 3, but exponents, in fact, are much more complicated and require higher level number theory than the scope of this lecture. But instead of replacing the exponent, we can again just replace the base. So 3029 raised to 1203 would be congruent to 9 raised to 1203 mod 10. And this is one of the cases where using negative numbers comes in handy, as we note that we can express 9 as negative 1 mod 10. And raising negative 1 to a power is a lot easier than raising any of these other two numbers. So it simply turns out, and as the power is odd, this simply turns out to negative 1 mod 10, which is once again congruent to 9 mod 10. So the last digit of 3029 raised to 1203 would be 9. And also as a side note, you can, many times for number theory, you want to check your answer. There's a especially good calculator called Wolfram Alpha, which is really good at calculating extremely large things if you want to check your answer. And as a whole, dealing with exponents in general is much harder since you can't immediately replace. And there are methods for dealing with them, but most of them are covered in high school math, including Fermat's theorem and the Euler-Toshin function, both of which are used in high school but are a bit too difficult for this lecture. But if you're interested in learning about them, we have some links on our handout, which you can check out after this lecture. Now we'll go into one of the ways that you can deal with them using some special properties using binomial expansions.
All right, so one method to approach exponents in mods is, like An said, the binomial expansion. So the binomial expansion involves, the given. So if you have something in the form of a plus b to the n, this is the equivalent of the sum of k equals 0 to n of n choose k, a to the k, b to the n minus k. So what this is equivalent is that this is equal to a to the n plus n times a to the n minus 1 b plus n choose 2, a n minus 2 b squared dot 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 all the way down to n times a b to the n minus first power plus b to the n. So we'll discuss this. So when we say n choose 2, this is a combinatorial function. We'll get into that more in our next lecture on combinatorics. But it's just the number of ways we can choose a group of 2 from n people, or a group of k things from a larger group of n. So let's put this formula to use. So let's say we want to find the last 2 digits of 21 to the 2019 power. So when we want to find the last 2 digits, this is equivalent of the question asking us to find the question mod 100, because whatever it is, mod 100 is just the last 2 digits. So we can't really simplify 21 like we did earlier, where we turned a really large number like 3029 into 9. Here we can't do that because 21 is obviously less than 100. So what we can do here is use binomial expansion. We can rewrite 21 as 20 plus 1. So it's in the form of our binomial expansion, a plus b. So we can write it as 20 plus 1 to the 2019 power. And what this becomes using our binomial expansion expands out to be 20 to the 19 plus 20 to the 19 plus 2019 times 20 to the 2018 times 1 dot 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 all the way down until 2019 times 1 to the 2018 times 20 plus 1 to the 2019. So something special you can see here is that all the terms, except for the last 2 terms, are multiples of 100 because they have some multiple of 20 squared. right? And 20 squared is 400, which is a multiple of 4, or which is a multiple of 100. So all of this is equivalent to saying that we can just ignore all of that because that's equivalent to 0 mod 100. So that means we only need to consider the last two terms. So we have 2019 times 20 plus 1. Well, using mods again, we can turn 2019 into just 19 because 2019 mod 100 is 19. So this just becomes 19 times 20 plus 1 mod 100. 19 times 20 is 380 and plus 1, so mod 100, which is the same as 80 plus 1, which is just 81 mod 100. So that means the last two digits of 21 to the 2019 power is 81. All right. So let's say, now let's say we want to find 3 to the 2019 power. Well, at first you might think, oh, we can do the same thing, just use binomial expansion. But we can see that since it's 3, there's no really nice binomial expansion because we can't write it as like a multiple of 10 plus a very small number. So like earlier it was nice because 20 is a multiple of 10, so we could just cancel out a lot of the terms. However, if we just list out a few of the terms in mod 10, so we know 3 to the 1 is just 3, 3 squared is 9, 3 cubed would be 27, which in mod 10 would be 7, then 3 to the 4th would be 81, which is 1 mod 10. So if we multiply 81 by 3, that's the same as multiplying 1 times 3 in mod 10. So we get 3 again. And you can see the next term would just be 3 times 3, which is 9, then 9 times 3, which would be 7, and then back to 1 again. And you can see that this pattern would just repeat on and on. So we can actually still use mods for this. So we can see that every 4, or the terms cycle every 4 terms. So 1 is always the 4th or 8th or multiple of 4th term, where everything that's mod 1 or everything that's 1 mod 4 would be 3, everything that's 2 mod 4 would be 9, everything that's 3 mod 4 would be 7, and anything that's 0 mod 4 would be 1. So the power is 2019, so if we take 2019 mod 4, it would just be 3 because the largest multiple less than 2019 is 2016. So we know that this would just be equivalent to saying 3 to the 3rd power, which would just be 7 mod 10. So this is just another way to approach these problems. You can find a pattern in the last digit. So oftentimes this only works if you're looking at the very last digit, because if you're looking at the last 2 digits, it becomes a much longer cycle.
Okay, so in addition to exponents, there's one more weird property that
All right, so next we'll be talking about modular inverses. So earlier we went over addition, multiplication, and exponentiation. But one thing we skipped over was something that is very basic, which is division. But division in modular arithmetic is a bit special because we can't exactly define it the same way as we do in normal arithmetic. So we can define division in another way. So let's say we want to find A divided by R. This is the same as saying we want to find A times 1 over R, where we can call 1 over R the multiplicative inverse of R because R times 1 over R is 1. And since we know what multiplication is, rewriting division as multiplication of A and 1 over R would just be much easier to solve. So in a similar way, we can define modular inverse, like let's say A to the negative first power mod n, such that A times A inverse would be 1 mod n. So to show how to use this, let's say we want to solve for 3x equals 5 mod 11. Well, in normal arithmetic, we would solve this by dividing both sides by 3. So in modular terms, we would just multiply both sides by the inverse of 3. So the modular inverse of 3 would be 4, because 3 times 4 would be 12, which is just 1 mod 11. So it's the same as saying we just multiply everything by 4. So this would give us 12x equals 20 mod 11. And this is just the same as saying x equals 20 mod 11, which is the same as saying x equals 9 mod 11. So if we play around a bit, we would notice that there's some pairs that don't have inverses. And this, so for example, let's say, what would the modular inverse of 2 in mod 6 be? Well, 1 times 2 is 2, that doesn't work. 2 times 2 is 4, that doesn't work. 2 times 3 is 0, that also doesn't work. 2 times 4 is 8, which is 2 again, that doesn't work. 2 times 5 would be 10, which is 4 mod 6, which also doesn't work. So it seems like none of these values work. And that's exactly true. 2 in mod 6 does not have any modular inverse. And specifically, it doesn't have an inverse because the greatest common denominator of 2 and 6 is 2 and not 1. So this comes to an important concept, is that the modular inverse of something exists only if the greatest common divisor of the number and the mod is 1. So how will we find the inverse? Earlier, we wanted to find the inverse of 3 in mod 11, and that was pretty easy because, 3 times 4 is 12. That's not too hard to think of. You can just test the values from 1 through 11. But let's say you want to find the mods of like the modular inverse of something in a very large mod. Well, last week we mentioned the Euclidean algorithm. So aside from just trial and error, we can actually use the Euclidean algorithm to find the inverse. So there's an extension of the algorithm which states that for any two numbers a and b, there exists some x and y such that ax plus by equals the greatest common denominator of a comma b. So for the inverse, we would be dealing with greatest common denominator, divisor of a and b is 1, since we want to find a mod b. So to find ax plus by equals 1, if we find the relevant x and y, we know that the modular inverse of a mod b and b mod a. So those would just be x and y respectively. So now the main question would be how to find it. So we'll demonstrate through a quick example. So let's say we want to find the inverse of 21 mod 11. So we'll start by forming a chain with division and remainders, similar to the Euclidean algorithm. So 100 equals 4 times 21 plus 16. So 21, the largest multiple of 16 that's less than 21 would be 1 times 16. So we would have 21 is equal to 16 plus 5. So the remainder is 5. So then what is 16 mod 5? That would be 1 because the largest multiple of 5 is 15. So it'd be mod 1. So remember in last week's handout, the process guaranteed to end at the GCD equals 1. Well, now we reverse the order. So we express the remainders in terms of larger numbers. So 1 obviously equals 16 minus 3 times 5. 5 equals 21 minus 16. 16 equals 100 minus 4 times 21. And now we can substitute 1 equals 16 minus 3 times 21 minus 16. So what we did here was that for 5, we substituted in 21 minus 16. Now, we can do this again. So we get that 1 equals or if we expand this, we get that 1 equals 4 times 16 minus 3 times 21. And this is equivalent to saying, since we know that 16 is 100 minus 4 times 21, it's 4 times 100 minus 4 times 21 minus 3 times 21, which is 4 times 100 minus 19 times 21. And this equals 1. So now that we see our values of x and y are 4 and negative 19, if we take the equation mod 100, we get negative 19 times 21 is congruent to 1. So that means negative 19 is the modular inverse of 21, and negative 19 mod 100 would be 81. So what you can see we did here is basically we found a value such that we expressed the mod times a multiple plus the number times a multiple such that their difference was 1, and then we took it in the mod. So that means the term with the 100, mod 100, completely disappears. And we can solve for a value where we get a number times our original number, which was 21, and this would equal 1. So our final topic is the Chinese Remainder Theorem. So the Chinese Remainder Theorem is a very important concept in competition math. It comes up very often, and at its most basic level, what it states is, let's say you had two mods that are relatively prime. Relatively prime meaning that they share no common factors. So let's say we want to find a number in the form of A mod P and B mod Q. The Chinese Remainder Theorem would state that if P and Q are relatively prime, meaning they share no factors, that means in mod P times Q, there's exactly one single solution for X. So for example, let's say we wanted to find a number that was both 2 mod 3 and 3 mod 5. Well, if we take the number in mod 15, there's exactly one solution. So the numbers that are 2 mod 3 would be 2, 5, 8, 11, 14. And the numbers that are 3 mod 5 would be 3, 8, and 13. As we can see, the only number they share in common is 8. So there's exactly one solution in mod 15 that satisfies both requirements. So the exact value of C comes out to be AQ times Q inverse mod P plus BP times the inverse of P mod Q. And all of this would be mod PQ. So we can take that expression in mod P and mod Q to verify, and we can see that it is equal to A mod P and B mod Q. So an example question. So you may, if you did the homework from last week, you may remember the problem where we had let n be the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2. So basically the concatenation of all the numbers from 1 through 44. So it tells us it's a 79-digit number, and that we want to find the remainder when it's divided by 45. So obviously we used our divisibility rules. We knew that if you took this mod 9, if you just added all the terms together, it would be a multiple of 9, since 1 plus 2 dot 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 all the way to, so it's a multiple of 9 if you added all the terms together, because, and if you take it mod 5, well, you can just look at the last digit, mod 5, which would just be 4 mod 5. So we know that it is, so we know that it is 0 mod 9, and that it is also 4 mod 5. So we want to find a unique solution in mod 45 where it is both 0 mod 9 and 4 mod 5. So we can use our formula earlier. So we want to find A times Q times the Q inverse plus B times the P inverse. So this would be 4 times 9 times the inverse of 9 mod 5, and 0 times 5 times the inverse of 5 mod 9. So this becomes, well, the modular inverse of 9 mod 5 would just be the same as the inverse of 4 mod 5. And we can see that its inverse would just be 4, since 4 times 4 is 16, which is 1 mod 5. So this is the same as saying 4 times 9 times 4. And since the second term has a 0, we just ignore that. So this becomes 4 times 36, which in mod 45 would be negative 36, which is equal to 9 mod 45. So that's our solution to last week's homework. It uses a bit more information than we taught you guys last week involving Chinese Remainder Theorem. So let's move on to some competition problems. So our first problem is we let S be the sum of the numbers from 2020 to 4040. So it asks us to compute S in mod 2020. So, well, if we take each term, instead of finding the sum and then taking mod 2020, we can instead just take all the terms individually mod 2020. That's so much easier, right? So this would just become 0 plus 1 plus 2 plus ... all the way back to 2019. And then finally, 4040 would just be 2020 mod 2020, which is also 0 mod 2020. So now we have a much more manageable sum. So the sum from 1 through 2019. If you go back to lecture 1 where we did arithmetic sequences and series, we know that the sum of the first n integers would just be n times n plus 1 over 2. So in this case, it'd be 2019 times 2020 over 2. And we want to find this mod 2020. So this becomes 2019 times 1010 mod 2020. But we can also rewrite 2019 as negative 1 mod 2020 because it's 1 less than 2020. So this is equal to negative 1010 mod 2020. And since negative 1010 mod 2020 is exactly half of 2020, this is the same as 1010 mod 2020. So that means our answer when this is divided by 2020 is 1010. So the next question asks us, what is the remainder when 1 plus 9 plus 9 squared plus ... plus 9 to the 2019 is divided by 10? Well, we can rewrite all this like before in mod 10. So we have 1, obviously, then 9. The 9 squared is 81, so mod 10 that would also be 1. And then 9 cubed would be 729, which is also 9. And then this pattern continues all the way up. But something special is you can see that this is kind of, we're not sure if this pattern will continue. I mean, it makes sense for it to. But a nicer way to think about this is if we rewrite 9 as negative 1 mod 10, this would just be 1 plus negative 1 plus negative 1 squared ... So this is just 1's alternating signs. So you get 1 minus 1 plus 1 minus 1 ... all the way until negative 1 to the 2019. Well, since negative 1 to the 2019 is negative, we just get 1 minus 1 plus 1 minus 1 ... and it ends with a 1 minus 1. So all of these should cancel out because you can pair each one with a negative 1. So this would be 0 mod 10. All right, so here we have a question that asks us to find an integer a between 0 and 14, such that 235, 835, 623 mod base 74 minus a is a multiple of 15 in base 10. So it asks us, what is a? So if you remember last week when we did bases, when we say something is written in base 74, what we can actually mean is that we can rewrite this as 2 times 74 to the 8th power, plus 3 times 74 to the 7th power, plus 5 times 74 to the 6th power, and so on, all the way down to 2 times 74 plus 3. Right? And you can see this is a bit similar to our last problem, where we have a bunch of powers of numbers. And it's also similar in that if you look at 74, which is the thing we're taking to a bunch of powers, if you take in mod 15, it's -1, just like how before we had 9 in mod 10 was -1. So what this gives us is that this would be equivalent to 2 times -1 to the 8th, plus 3 times -1 to the 7th, plus 5 times -1 to the 6th, ... all the way down to 2 times -1 plus 3. And this is just means that we'll be adding and subtracting alternating terms. So what this boils down to is 2 minus 3 plus 5 minus 8 plus 3 minus 5 plus 6 minus 2 plus 3. And if you sum these together, 2 minus 3 is -1, plus 5 is 4, minus 8 is -4, plus 3 is -1, minus 5 is -6, plus 6 is 0, minus 2 is -2, plus 3 is 1. So this would just be 1 and mod 15. So since we want to find a such that this number minus a mod 15 is 0, that means a would also be 1 mod 15, because 1 minus a equals 0, meaning a would be 1, since 1 minus 1 is 0. So that means a is 1, because a has to be between 0 and 14. So our next question, given that m and n are positive integers such that m is congruent to 6 mod 9 and n is congruent to 0 mod 9, what is the largest integer m times n is necessarily divisible by? So since m is 6 mod 9 and n is 0 mod 9, if we multiply it to m times n, that would just be 0 times mod 9, right? Since it's 0 mod 9, that means it's divisible by 9. So our answer would be 9, right? Well, not exactly, because although it is divisible by 9, this does not necessarily mean that 9 is the largest number that divides mn. So let's take a step back. Before we multiply them together, let's look at each term individually. So let's look at m. m is 6 mod 9, right? So what's the largest number that necessarily divides m? Well, that's the same as saying, what is the largest mod m such that m mod that mod is 0? Well, we can see that would be 3, because m is always divisible by 3, because 6 mod 9 would be divisible by 3, because it can be expressed as 9x plus 6, which is a multiple of 3. Now, let's look at n. Well, n is 0 mod 9, so obviously that means the largest number that divides n would be 9. So that means that since 3 divides m, and 3 is the largest number that divides m, and 9 is divisible by 9, or 9 divides n, and n is the largest number that divides n, that means 27 has to be able to divide n times m, and 27 is the largest number that divides m, n. So yes, although mn is 0 mod 9, that doesn't necessarily mean it's our solution. And we, in fact, did find a larger number that divides mn. And that would be our final answer, which is 27. And a special property that this problem showcases is that if you have a number, let's say a mod b, the largest number that divides m, let's say m is a mod b, would be LCM of a and, or GCD of a and b. So here we have two brothers took X cows to a market and sold them each for X dollars. After selling the cows, they divided up money by giving 10 to the older brother, 10 to the younger brother, 10 to the older, 10 to the younger, and so on. At the last division of money, the older brother received $10, while the younger brother received less than $10. How many dollars must the younger brother have received at the last division? Well, at first, this problem might seem very confusing. I mean, we don't even know how many cows were sold. So how are we supposed to know how much money the younger brother received? But let's slow down. So let's first think about this problem in terms of mods. So since we're splitting it between an older brother and a younger brother, this repeats every $20 after 10 goes to each brother. So we can take this in mod 20. And since at the last division, so everything before the last division is a multiple of 20. So what we only care about right now is the last division. We know that the older brother received $10, and let's say the younger brother received K dollars. So we can write this as 10 plus K, and this is obviously less than 20, and we can take that this mod 20 is congruent to the total amount of money they got, mod 20. So now, we want to find a number x squared such that in mod 20 it is in the form 10 plus k. So we can go about this by just writing out all the squares in mod 20. So 1 squared, or 0 squared, let's start off with, would be 0, obviously. 1 squared would be 1. 2 squared would be 4. 3 squared would be 9. 4 squared would be 16. Now 5 squared would be 25, but that mod 20 is 5. And then 6 squared is 36, which mod 20 is 16. Then 7 squared is 49, which mod 20 is 9. And then we have 64, which is 4 mod 20. Then 81, which is 1 mod 20. Then 100, which is 0 mod 20. Well, we could see there's a bit of symmetry here, right? Well, actually, we don't even need to write out the rest of the terms, because if you think about 11 mod 20, that's the same as saying negative 9 squared mod 20. So if you square both sides, 11 squared is the same as 9 squared. And since we already know 9 squared is 1, so this won't yield any new values. So we basically just reflect this across. So our next terms will be 1, 4, 9, 16, 5, 16, 9, 4, 1. All right. So now we look at these and we notice that there's actually only one value that can be expressed in the form 10 plus k mod 20, and that would be 16. Although there are multiple values that give you 16, that doesn't really matter for us. We just want to know what k is, not what x is. So we can see that if we set 10 plus k to be 16, that means k would have to be 6. So that would be our answer. K is 6. And we can see that this gives us a pretty interesting thing where we don't even need to know what x was, but since there's only one possible value, we found k despite having no idea what x is. Now, here we have a more difficult A and C question. So it tells us let A1, A2, dot, 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 all the way until A of 2018 be a strictly increasing sequence of positive integers, such that A1 plus A2 plus dot, 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 plus A 2018 equals 2018 raised to the 2018 power. And asks us what is the remainder when A1 squared cubed plus A2 cubed dot, 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 plus A 2018 cubed is divided by 6. Oh, that's pretty intense. I mean, 2018 to the 2018 power is huge, and then it asks us to find the sum of the cubes of all the terms. Like, how are we even supposed to do this? So, you know, it's easy to get overwhelmed by these types of problems, but what it's good to always do first is just rewrite this in terms of mods. So it asks us to find the remainder. So we want to find A1 cubed plus A2 cubed plus dot, 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 plus A 2018 cubed mod 6. So we know we want to find that. All right, so that's helpful a bit. It makes it more manageable, but don't really see how that helps us. So why don't we try something? Let's say A1 was 1 mod 6. Well, then obviously A1 squared or A1 cubed would be 1 mod 6 because 1 cubed is 1. All right, so let's do this. If let's say H1 was 2 mod 6, well, 2 cubed would be 8, which would be 2 mod 6. When we do this with 3 cubed would be 27, which mod 6 would be 3 again. All right, so we're starting to see a pattern here, right? If we do this with 4, we get 64 mod 6, which is 4. All right, then 5 cubed would be 125, which would be 5 mod 6, right? Ooh. And then obviously 6 or 0 mod 6, 0 cubed is 0 mod 6. So, all right, we found something very interesting. Regardless of what the number is, if you cube it in mod 6, it stays the same. So what this is essentially saying is that instead of writing as A1 cubed, A2 cubed, and A2018 cubed, right, mod 6, we can actually replace all these with just their terms, which will be A1 plus A2, mod 6. And since the problem already told us that this is 2018 to the 2018, we just want to find 2018 to the 2018 mod 6. All right, we know that 2018 mod 6 would be 2 because 2016 is a multiple of 6, so 2018 minus 2016 is 2. All right, so now we can do one of our strategies from earlier. We could do binomial expansion, but what we could also do is just write out the terms. So we know that 2 squared is 4. And 2 cubed is 2. Then 2 to the 4th would obviously just be 2 times 2. Then 4 times 2 would be 2 again. Then 2 times, so we can see that this alternates, right? So the even powers of 2 are 4 mod 6, and the odd powers of 2 are 2 mod 6. And we can see that 2018 is obviously even. So if we take an even power of 2 mod 6, we know that that's equal to 4. So we get our answer that this is 4. Yeah. And this problem actually gives you a bit of misleading information. It tells us that it's a strictly increasing sequence of positive integers. And we actually have no use for that whatsoever. And this is just kind of to mislead you, because the point, I guess the most difficult part of the problem is just like how intimidating it looks, because you have such a large value and you want to calculate an even larger value. Like, you don't really have any way to approach this, except when you take mods and you make a key observation, it actually becomes very simple. So moving on, our next question, this was from your own South Math Club. It asks us to find a remainder when the product of all the odd numbers from 1 or less than 2019 plus the product of all even numbers less than 2019 is divided by 2019. Well, what we can see here is, well, this is pretty weird. We don't really know how to approach this, but you remember earlier, you can notice how we can rewrite 2018 as -1 mod 2019, and we can rewrite 2016 as -3 mod 2019. We see that actually all the even numbers correspond to an odd number, just negative. So actually, we can rewrite the second product, 2 times 4 times 6 ... as negative 2017 or negative 2017 times negative 2015 times negative 2013 ... times -1. So our two products have the same magnitude because, well, they are the product of all the odd numbers less than 2019. However, if you look at our second product, we know that how many terms are there? So if you think, so 2, 4, 6, 8, the number of terms would just be 2018 divided by 2. So there are 109 terms. Since the number of terms is odd, that means since all the numbers in there are negative, that means the entire product will be negative. So what we get is that in mod 2019, this is just 1 times 3 times 5 dot 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 times 2017 minus 2017 times 2015 times 2013 dot 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 negative times 1. And these two products are the same. So when you're subtracting the same thing from each other, it's 0. So actually all this just cancels out and we get that our answer is 0. So next it asks us, our next question is asking us for the remainder when 7 to 2010 is divided by 100. All right. So, well, we can't really test out the terms because if you test it out, you get like 7, 49, 43, and so on. It's not very nice. It's not really a short cycle because you have 100 possible or 100 possibilities for the last 2 digits or the remainder when divided by 100. So our sort of finding a pattern in the last few digits doesn't really work in this case, right? And 7 isn't really a nice number to do binomial expansion. I mean, you could do 10 minus 3 to 2010, but that's not very nice. But if you notice, earlier when we wrote out our numbers, right? Notice how 49 is actually 1 less than a multiple of 10. It can be written as 50 minus 1. So actually, this is actually not a bad number to do binomial expansion on. We have a multiple of 10 minus 1. So we can rewrite 7 to the 2010 as 7 squared to the 1005 power. So this would be equivalent of 50 minus 1 to 1005 power. So what we can do here is we can binomial expand. So since we only need to look at the last 2 terms, we get that the last 2 terms would be 1005 times 50 minus 1. So if you take this mod 100, this just becomes 5 times 50 minus 1, which becomes 249, which mod 100 would be 49, and that's our answer. An alternative solution to this would be, after noticing that 7 squared is 50 minus 1, you can square that again, and you actually get that, well, since 50 is exactly half of 100, 50 minus 1 squared becomes, well, 50 squared times 2 times 50, which is 100, which conveniently is 0 mod 100, plus 1. So 7 to the 4th power is 1 mod 100. So that means we can just find 2010 mod 4 and find the equivalent. So it's the equivalent of 7 squared mod 100, because 2010 mod 4 is 2. And we can see that this gives us the same answer, which is 49 mod 100. So our next question, how many zeros occur at the end of 1999 to the 6th power plus 6 times 1999 plus 5? Well, I guess in one sense, this problem is a bit more straightforward than last, because we can obviously see that 1999 is just 2000 minus 1, and that's a very nice number for binomial expansion. So we can rewrite this as 2000 minus 1 to the 6th power plus 6 times 2000 minus 1 plus 5. So using a binomial expansion, this becomes 2000 to the 6th power minus 6 choose 1, which is 6, times 2000 to the 5th power. And there's a minus because we multiply by -1 to the 1st power. However, we're going to omit that because it just takes up some more space. So the next term would be positive again, and it'd be 6 choose 2, which if some of you guys memorize Pascal's triangle would be 15. So it'd be 15 times 2000 to the 4. And then our next term would be minus 20 times 2000 to the 3 plus 15 times 2000 squared minus 6 times 2000 plus 1. So this should just be from the first term. And then our second term would become plus 6 times 2000 minus 6. That's from our second term, 6 times 1999. And finally, we would have plus 5, which is from our very last term. Well, as you can see, some things cancel out. The 1 minus 6 plus 5 obviously cancel out. And we notice we have a minus 6 times 2000 and a plus 6 times 2000. So those cancel out. So all we're left with is this end, right? So we can notice that of all of these, the term with the least number of trailing zeros will be the limiting factor. And there's only one single term with the least number of trailing zeros, and that would be the last term, which is 15 times 2000 squared. So that means we're going to find the number of zeros in 15 times 2000 squared. So at first glance, you might think, oh, you have 2000 squared, so that's 3 zeros. You square it, so it's 6 zeros and 6. But actually, you can rewrite this. If you move one of the 2's from one of the 2000s to the 15, this becomes 30 times 2000 times 1000, or times 1000 times 2000. And here we can see there's 1, 2, 3, 4, 5, 6, 7 zeros, and this would just become 60 million. So that means that the number of trailing zeros on this expression would be 7, and that would be our final answer. All right, moving on. So here's another problem. So determine the smallest integer m such that m squared plus 7m plus 89 is divisible by 77. Well, at first glance, you might think of trying to factor this and solving it in mod 77. But there is a very important property about quadratics in mods. And this is very important because it can very easily lead to like silly mistakes or just downright wrong answers. So thing is, if you have a quadratic in a mod, unless the mod itself is prime, so like let's say mod 13, if it's prime, you're allowed to factor it. However, it's not, you're not allowed to. And this stems from the fact that if you factor it, solving for the zeros implies that at least one of the terms has to be 0. However, if the mod is not prime, that isn't necessarily true. And like some of you have noticed, 77 is obviously not prime. So what we can do here is actually very common in a lot of math competition problems, which is use the Chinese Remainder Theorem to come up with 2 other requirements. So initially we said that given 2 properties, like A mod B and A mod P and B mod Q, we can find a unique solution in PQ. But what this also implies is if we want to find a solution in, let's say, mod 77, we can just find the corresponding solutions to 7 and 11. So we want to find something that is 0 mod 77. And this is equivalent to finding an integer m that satisfies that this quadratic is both 0 mod 7 and 0 mod 11. So if we were to take this mod 7, well, m squared plus 7m plus 89, well, since it's mod 7, we can do our factoring. And another useful thing about mods is that you can actually get rid of a lot of terms. As you can see here, well, 7m is 0 mod 7, so that becomes 0. And 84 is 5 mod 7, because 84 is a multiple of 7, so 5 mod 7. So this just becomes m squared plus 5 equals 0 mod 7. So that means m squared equals -5 mod 7, which is just 2. So if we test out values for finding m squared, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, which is 2 mod 7, so 3 works. 4 squared is 16, which is also 2 mod 7, so that works. 5 squared would be 25, which would be 4 mod 7, and 6 would be 36, which is 1 mod 7. So 3 and 4 both work. So we have two solutions in mod 7, which is 3 mod 7 and 4 mod 7. Now let's consider mod 11. We have the same quadratic, m squared plus 7m plus 89. And we want to find this mod 11. Well, we can rewrite this as m squared plus 7m. And you could change this all the way down to plus 1. But if you notice, if we leave it as a plus 12 instead, this is actually much more easy to factor because you can have it as m plus 3 times m plus 4. So this gives us our two solutions in mod 11, which are -3 and -4. Now, using Chinese Remainder Theorem, that means we have two possible mods in 7 and two possible mods in 11. So that leaves for 4 distinct solutions in mod 77. If we were to try and figure this out, we can use our formula, but the solutions would just be respectively 18, 52, 73, and 74 mod 7. And we want to find the smallest one, so we would obviously take 18, and that would be our answer. M equals 18. All right. We have time for, I think, 1 or 2 more questions. So this is a much more difficult AMC question. So we have the number obtained from the last 2 non-zero digits of 90 factorial is equal to n. What is n? So this problem will be using a lot of the concepts we learned this week and in previous weeks. So first, we want to find the last 2 digits of 90 factorial that are not 0. So first, let's find how many zeros follow 9. So the number of zeros is basically the number of times 10 can divide into 90 factorial, which is just the minimum of either the number of times 2 divides into 90 factorial and 5. And since 90 factorial has a lot more powers of 2 in it, you just want to find the number of 5s that divide into 90 factorial. So we can rewrite all the multiples of 5 as like 5 times 15 ... times 90. And we can see that they're exactly, in this case, 18 multiples of 5. But there's something you need to watch out for is that this multiples also include 25, 50, and 75, which are multiples of 25 as well. So each of those 3 has exactly 1 more multiple of 5 to them. So we add 3. So this gives us 18 plus b, which is 21. So there are 21 zeros at the end of 90 factorial. So let's call n a variable n. Let's call n be 90 factorial divided by 10 to the 21. So we want to find n mod 100 because we want to find the last 2 non-zero digits. So to do this, we use our principle of Chinese Remainder Theorem again. So we can split this up into 2 problems. We want to find n mod 4 and n mod 25. And this will give us our solution in n mod 100. So let's do n mod 4 first. It's really easy since, well, 90 factorial has more multiples of 2 than 10 to the 21 by a lot, actually. N would obviously be 2 to something power in it, which would be more than 4. So n mod 4 would just be 0. Now, we'll go on to the more difficult part, which is n mod 25. So one of the key observations to the problem was that, well, first, let's ignore all the multiples of 5. Since 90 factorial over 10 to the 21, we kind of like divided out all of the multiples of 5. So let's ignore this first. Let's look at the non-multiples of 5 in 90 factorial. So you have 1, 2, 3, 4. If you multiply those together in mod 25, you get 24. And that's -1 mod 25. All right, so let's look at the next group of 4 numbers. So it'd be 6, 7, 8, 9. Well, that would also conveniently be 24 mod 25 if you calculated it, which would be -1. And actually, any number in the form of 5k plus 1 times 5k plus 2 plus 5k times 3 times 5k plus 4 would actually become 24 equals -1 mod 25. And you can expand this. You'll see that this always remains true. So since so we can actually group the numbers of 90 factorial into groups of 4, and we can see there are exactly 18 of these groups. You have like 1 through 4, 6 through 9, dot dot dot, all the way until 86 through 89, and there are exactly 18 of these. So all the non-multiples of 5s in 90 factorial, this just becomes -1 to the 18th power, which would just be 1. So we can effectively just ignore all of these in the product. So now all we're left is the multiples of 5 over 10 to 21. Well, since we know that there's exactly the same number of 5s in 10 to the 21 as well as 90 factorial, we can rewrite the multiples of 5 in 90 factorial, which were originally like 5, 10, 15, dot dot dot, all the way until 90. We can actually rewrite this as 1, 2, 3, 4. And watch out for the next one, because the next one is 25. And remember how we divided by 25? We divided by 5 twice. So this actually would be 1. And then it would be 6, 7, 8, 9, 3, 2, 10, 11, 12, 13, 14, 3, and 15, 16, 17, or 16, 17, 18. There. And we can see we have like the 1, 2, 3, 4, 6, 7, 8, 9s again. So there are exactly 3 pairs of those. So that becomes -1 to the 3rd power times 1 times 2 times 3 times 16 times 17 times 18. And if you were to multiply this out, you would get -1 times 21 times 6, which would be -126, which would be -1 mod 25. All right, so now we have somewhat of an answer, but if you remembered, what we're trying to find is 90 factorial divided by 10 to the 21, not 5 to the 21. So we have to take -1 mod 25 and divide it by 2 to the 21st power. Well, first, let's start by simplifying 2 to the 21st power. 2 to the 21st power is not a nice number. So we can observe that actually 2 to the 10 power is 1024, which is -1 mod 25. So that means we can rewrite 21 as 2 to the 10 squared, which would be -1 squared, times 2, which would just be 1 times 2, which is 2. So effectively, what we're trying to find is -1 mod 25 divided by 2. So we can rewrite -1 as 24 mod 25. And in this case, since 2 is relatively prime to 25, we can actually just do straight up division in this case, instead of having to find the modular inverse. So it'd be 24 divided by 2, which is 12. And that would be our value for n mod 25. So we know that our number is both 12 mod 25 and 0 mod 4. And we can see that this is actually very easy to find in mod 100. We can just say it's 12 mod 100 because 12 is a multiple of 4, so it's 0 mod 4. And 12 mod 12 is also mod 12 mod 25. So that means our answer is actually just 12. The last two digits of 90 factorial that are not 0 are 12. So this is definitely a very difficult problem. It's probably nothing that will show up on like anything middle school math, but it brings together a lot of the concepts that we used, not just within this week's lesson, but the previous weeks. And it really develops like critical thinking and just being creative.